Today we're going to talk about section 9.3, which is going to give us two new tests for determining if a series converges or diverges. So those tests we're going to learn today are called the integral test and the p-series test. The integral test can be used only under certain conditions. We'll talk about those conditions. If the sequence is a positive sequence, and if we were to look at its corresponding function, if that function were continuous, positive, and decreasing for n greater than or equal to 1, then the series, whatever the series does, would be the same thing as whatever its corresponding improper integral does. They would either both converge or both diverge. A little generic picture here of a sequence. So if your terms were x1, x2, x3, x4, the corresponding function would be f of x. So an example, apply the integral test to this series to see if it converges or diverges. So let's consider the graph for this function that corresponds with an x over x squared plus 1. And you can see from the graph that it is positive, continuous, and decreasing from 1 to infinity. So since those conditions are met, we can go ahead and use the integral test. We're going to look at the corresponding improper integral from 1 to infinity of x over x squared plus 1. And of course, I want you to rewrite that as the limit as b goes to infinity of the integral from 1 to b. And if we did a little u substitution, we would see that the antiderivative here is the natural log of x squared plus 1 over 2. Fundamental theorem, we're going from 1 to b, so this becomes 1/2 natural log of b squared plus 1 minus natural log of 1 squared plus 1. Remember, we're considering the limit as b goes to infinity. So think about what would happen here. Natural log of 1 squared plus 1, of course, is a number, but what does the natural log function do as b goes to infinity? That goes to infinity. So since the integral diverged, the integral test tells us that the series also diverges. You need to remember to write reasons whenever you're doing these problems. So you would say that the series diverges by the integral test. Okay, next problem. Use the integral test to determine the convergence or divergence of this series. I really want you to consider, is the criteria for the test met? And notice that here's a graph of it. It is positive, decreasing, and continuous. Remember, this is the graph of the corresponding function. This would be the function 1 over x squared plus 1. The function is what we're looking at. We're going to do the integral of that function from 1 to infinity. I'm going to rewrite that as the limit as b goes to infinity from 1 to b. And you should recognize the antiderivative for 1 over x squared plus 1 is arctan of x. Apply the fundamental theorem to that. And remember, I said arctan is going to come up a lot in this chapter, so you need to really make sure you remember what the graph of arctangent looks like. As b goes to infinity, as a horizontal asymptote at y equals pi over 2, the limit for this is pi over 4, because for arctan of b, that's pi over 2, minus arctan of 1, which is pi over 4. So pi over 2 minus pi over 4, we get pi over 4. So since the improper integral converged, that means our series also converges by the integral test. Now, one really important point here I want to make. This does not mean that the series converges to pi over 4. In other words, the infinite sum for this series is not pi over 4. In fact, we don't know what the infinite sum is for this. There's very few series we're going to work with where we can actually calculate the infinite sum. Usually, if that's the case, it's either geometric or telescopic. But what this tells us is that the series converges. The improper integral converges to pi over 4, and that's nice, but that just tells us that the series converges. We can't say it converges to pi over 4. It's a really important point, so make note of that. Okay, so the next thing I want to talk about is another common type of series we'll come across, which is called a p-series. So a p-series is a series in the form 1 over n to some power p. P just has to be a positive constant. Be a fraction, be a radical, I suppose, but it just has to be positive. We've kind of already talked about what happens if p equals 1. I made mention to it the first day. That turns into what we call the harmonic series. It's probably the most common p-series that comes up. So 1 over n, just the series 1 plus 1/2 plus 1/3, etc. So let's use our integral test to see whether p-series converge or diverge and under what conditions. So note that as long as p is positive, the values of this sequence will correspond to a function that is always positive, continuous, and decreasing. So think about what we'd be working with here. 1 over x, 1 over x squared, 1 over x cubed. Those functions are always going to be positive, continuous, and decreasing from 1 to infinity. So since that applies, we can use the integral test. So if we look at the integral from 1 to infinity of 1 over x to the p dx. Now, we've actually seen this before. We saw this in an exercise back when we were doing improper integrals in the last chapter, and we talked about under what conditions this would converge or diverge for certain p-values. So I'm going to write this as x to the negative p. And we're going to rewrite this as the limit as b goes to infinity. So p, remember, is a constant. So this turns into x to the negative p plus 1 over negative p plus 1 from 1 to b. And remember, the b and the 1 go in place of the x. P is a fixed constant here, so we're going to apply the fundamental theorem of calculus and we get this expression. So think about what happens here. If negative p plus 1, right here, comes down to this exponent. If this exponent stays negative, then what does that do to the b? Sends b to the denominator, and it leaves me with this constant over here, which means it converges. So in order for negative p plus 1 to be negative, p would have to be greater than 1. On the other hand, if p is less than or equal to 1, then this fraction will blow up and get bigger, and the series would diverge. So this is the test for the p-series. This is what you need to make sure you pay attention to. So when you have a p-series, if p is greater than 1, then we're going to have a converging series. If p is less than or equal to 1, then we're going to have a diverging series. So this is nice. This makes a really easy test to use. Take a look at this example. So we have this series 3 over square root of n. And of course, note that that is a p-series because that could be 3 over n to the 1/2. In this case, p is 1/2, less than 1. So based on the rules we just mentioned, that means that p, or the series, diverges. On the other hand, look at this series. So this could be written as 7 over n to the 5/3. So p is 5/3. And again, based on the rules of the p-series, we would say this converges. Your reasoning for this converges by p-series, p is greater than 1. Okay, the last thing I want to talk about today, suppose you were asked to find the infinite sum S for a series. Let's just look at an example here. We've got 2/3 to the n. And hopefully by now you recognize that that's a geometric series and r is less than 1, so we know it has an infinite sum. And that would be equal to a over 1 minus r. So that just gives us an infinite sum of 3. On the other hand, what if you were asked to find the nth partial sum for this series? Remember, with geometric, we actually had a formula for the nth partial sum of a geometric series. Remember, that was S of n was equal to a times 1 minus r to the n over 1 minus r. And let's suppose we were asked to find the fifth partial sum. Say we were asked to find S sub 5. So we could use this formula, plug in 5 for n, and again, this is only because it's geometric, I have this special formula. But if we plugged in 5 for n, get your calculator out and verify that you get 2.6049. So the difference between S, the infinite sum, which was 3, and S sub 5, the partial sum, we call the remainder. This is very important. Make sure you understand what's going on here. The notation we use is R sub 5 because we're using the fifth partial sum. But do you agree then that R sub 5 would be infinite sum minus the fifth partial sum? So in this case, that would be 3 minus 2.6049, which leaves us with a remainder of 0.3951. In general, if we know a series converges to some infinite sum S, then our remainder would be expressed by S minus S sub n. Okay, so what we want to be able to do when we're working with these problems, we don't always know what the infinite sum is. Remember I mentioned earlier that usually it's only geometric and telescoping that we can actually obtain an infinite sum. We know they converge most of the time, but we don't know what the infinite sum is. So this remainder idea is very important because it's going to tell us how many terms we need to use to get close or within a certain amount to an infinite sum. So the PowerPoint says, let's prove that if f is positive, continuous, and decreasing, so the functions we've been working with in this PowerPoint, then the remainder, R sub n, is bounded by this expression. The remainder is positive, and it's less than or equal to integral of the function from n to infinity, where n is whatever number you used for your partial sum. Now, I'm going to skip the proof right now because I think it's a little hard to do in the video. We're going to do it in class as a warm-up. But I want to show you what we're going to do with this and how we're going to be using this expression to approximate remainder. You might get a question that looks like this. Approximate the sum of the convergent series using 4 terms and estimate the maximum error for your approximation. The series we're working with is 1 over n to the 5th. So notice here that this is a p series where p is 5. And like we talked about earlier, since p is 5, that's greater than 1, we know this is going to converge. The question is, the problem is we don't know what it actually converges to. So we're going to approximate the infinite sum, and we're going to do so using 4 terms, or the fourth partial sum. So in your calculator, you can either do it by hand or you could use that summation feature in your calculator. If we were to add up the first 4 terms, starting with n equals 1, going through n equals 4, we would get the fourth partial sum to be 1.0363. So what that remainder that you got down from the last slide, what that remainder said, was that remainder was bounded by the integral from 4 to infinity. I'm using 4 because we were using 4 terms. We were working with the fourth partial sum. So we're going to evaluate this improper integral just like we always have. So we're going to write this as the limit as b goes to infinity from 4 to b. We're going to find the antiderivative. If we apply the fundamental theorem of calculus, we're going to have negative 1 over 4b to the 4th minus negative 1 over 4 times 4 to the 4th. And that first term would zero out because b goes to infinity, and it's going to leave me with this value. So what this tells us is that our approximation of the infinite series using only 4 terms was within 0.0010 of the actual infinite sum. Now we don't know what the actual infinite sum is, we can't figure it out, but we know that our approximation using 4 terms was this close to it. Okay, let's do one more. Find capital N such that the remainder is within 0.001 for this convergent series. So this time they're going backwards. They're saying, you figure out how many terms you need to use to get to a remainder this close. What I'm going to do is I'm going to write the improper integral here from n to infinity using the function 1 over x to the 3 halves, and I'm going to make a little inequality out of it and say I want that to be less than 0.001. I'm doing this because, remember, we said the remainder is less than the integral from n to infinity. So we want that integral to be less than 0.001. And we're going to rewrite this as the limit as b goes to infinity from n to b. Using the fundamental theorem, we get this. We put in b and n. And when we took the limit as b goes to infinity, the first term zeroed out, but the second term had an n in it, and it was positive because we did minus a negative, and we get this expression. Then we want to solve this inequality. We're going to multiply and divide by the 0.001, we get this. How do we solve for n here? Square both sides, and we get this. So what this means is, in order for our summation to be within 0.001 of the actual infinite sum, we would need to calculate 4 million terms, or the 4 millionth partial sum. Now, obviously, I'm not going to ask you to do that because that would take a long time in a calculator to figure out. But you can see that this series grows much slower than the one in the last example. In that case, it only took 4 terms to get within a certain remainder. This one takes 4 million.